Welcome all, I am Ahmed Baba and I'll be presenting our work compacting points to sets through object clustering. This is a joint work with Yule Sui. In short, we aim to map points to targets or memory objects to integer identifiers in such a way that we use as little space as we can in a bit vector representation of points to sets. First, a quick overview of PointsTo Analysis. The aim of PointsTo Analysis is to determine what each pointer may point to at runtime. The result is a so-called points to set for each pointer containing the possible points to targets or memory objects. Bit vector representations of these sets have been successfully and widely deployed in mainstream PointsTo Analysis. Some clients of PointsTo Analysis include bug detection, optimization, and instrumentation. A PointsTo Analysis can be tuned such that it considers the flow of control, calling context, fields separately, and more. Generally speaking, a more precise analysis is more expensive, so performance improvements are always welcome. For this work, we'll be focusing on bit vector representations of points to sets and flow-sensitive analysis, specifically staged flow-sensitive analysis. In its most basic form, a flow-sensitive analysis would use the control flow graph of a program directly to account for the program's control flow. This is expensive. Staged flow-sensitive analysis, or SFS, makes this much cheaper. In it, we first perform a fast auxiliary analysis, like a flow-insensitive Anderson's analysis. Then, using those results, we build an over-approximate memory SSA form, and with that, we build a diffuse graph, and finally, we perform the analysis atop this diffuse graph rather than the control flow graph. For our work, this analysis is our main focus. Our work focuses on compacting points to sets, but why do compact points to set representations matter? Here are some statistics for some real-world C and C++ programs. Each top-level variable has a points to set associated with it, and each memory object has at least one. In fact, each memory object can have a points to set per program point. Despite SFS significantly reducing this, the number is still large. PointsTo Analysis centers around unions between points to sets, and the number of unions can grow into the billions, so improving them even slightly can be useful. Finally, the points to sets themselves are not necessarily small and can have many elements. Their storage takes memory, so a more compact representation will improve the situation. Continuing with some background, what is a bit vector? A bit vector is a string of bits implemented as an array of words, or the native integer size, that represents a set of integers. Given a bit vector, if a bit is set in the bit vector, the index of that bit is a member of the set. Otherwise, it is not. As an example, consider the set containing 0, 3, 8, and 9. For simplicity, we use a word size of 4 for all of our examples. We see that the indices of the set bits correspond to the members of our set. In this example, we require 3 words instead of the 4 that would be if we represented each member as a word explicitly. The union operation is fundamental to PointsTo Analysis, and bit vectors provide fast unions. Simply, given 2 bit vectors, the resulting union is made up of the result of the bitwise OR operation between each pair of words. This is extremely amenable to vectorization, has good spatial locality, and is compact. Neither operands nor the result require much metadata to fiddle with. One downside of bit vectors is the wasted space in the form of 0 words. Unset bits are practically dead space. This can be solved through sparse bit vectors, which we discuss in our paper. Another way to partially solve this is through stripping trailing zeros and instead maintaining the length of the array containing the words, as many implementations do. We also further strip leading zeros by maintaining an offset indicating what the first bit represents. We refer to these bit vectors as core bit vectors as only the core remains. For example, consider this set containing large integers. Before stripping leading zeros, we would have many 0 words which do nothing but indicate the absence of members. Instead, we can maintain an offset indicating what the first bit represents and a length for the array which for brevity we show implicitly. This takes small constant space for metadata, an offset, and a length, and unlike sparse bit vectors, maintains the benefits of standard bit vectors when performing unions. A union algorithm is available in our paper. From here, we refer to standard bit vectors as those which strip trailing zeros and core bit vectors as those which strip leading and trailing zeros. In order to use bit vectors as points to sets, we need to map our memory objects, or points to targets, to integral identifiers. For example, consider a points to set containing objects 04, 05, 012, and 014. A naive mapping would be to map each object according to its subscript, and similar mappings are common in real-world implementations. As a core bit vector, this mapping causes the points to set to require 3 words. Let us consider a more contextually wise mapping. Mapping 04 to 4, 05 to 5, 012 to 6, and 014 to 7. The result is that the points-to set fits in one word as a core bit vector. More generally, given a points-to set with n objects and a word size of w, the ceiling of n divided by w is the minimum number of words required to represent that points-to set as a bit vector, that is, given a perfect mapping. For example, this set of 5 elements requires at minimum 2 words to represent when the word size is 4. We observe that objects which appear in the same points-to set should be mapped to numerically close identifiers to prevent large swathes of unset bits in bit vector points-to sets. The problem is that points-to analysis is unpredictable. We don't know which objects will appear in the same points-to sets. However, in a staged analysis like SFS, the auxiliary analysis soundly over-approximates the main analysis. That is, points-to sets in the main analysis will be subsets of those in the auxiliary analysis. So intuitively, a good mapping for the auxiliary analysis will be good for the main analysis, or at least wiser than a random mapping. Our results show that this is the case in practice. This sounds like an optimization problem, and one in which integer linear programming can give us an optimal solution for. We attempt to generate the best possible core bit vector representation for the auxiliary analysis. To frame this as an integer programming problem, we say that each points-to set P with objects O subscripted by X further subscripted by an index has known and unknown variables. The known variables are n, which is the number of objects in P, and small w, which is the least possible number of words required to represent P as a bit vector. For unknown variables, we have m subscripted by x subscripted by I, which represent the map to identifiers of the corresponding object O, and we have some f, which is an offset multiplier for where the m identifiers may start, or the least possible identifier. Based on this, we generate constraints for every points-to set P. Each mxi should be greater than or equal to the offset multiplier fp multiplied by the word size, in other words, the smallest possible identifier in this points-to set. And also, mxi should be less than that smallest identifier all the way up to the largest possible identifier in the best case representation of P. That is, mxi is within some range of size small w for P. The offset multiplier should be greater than or equal to 0 as we don't want negative identifiers. We also need to ensure the mapping is one-to-one. No two objects should map to the same identifier, and neither should two identifiers map to the same object. The absolute value function is not linear, but can be linearized. Unfortunately, these constraints may be impossible to solve in some cases due to the pigeonhole principle. Let us consider these 3 sets, P1 containing O1 and O2, P2 containing O1, O3 and O4, and P3 containing O2 and O5. We want O1 to be close to O2, O3 and O4 because O1 appears with these objects in P1 and P2. But we also want O2 to be close to O1 and O5 because it appears with them in P1 and P3. With a word size of 4, small w is 1 for all sets. However, the sets overlap, and we have 5 objects in total. A word can only contain 4 bits, not 5, and so the pigeonhole principle makes solving this impossible. To solve this, we add a tolerance to the range which our identifiers can fit in. Obviously, this is trivially solvable with astronomical tolerances, so we optimize for a minimum sum of tolerances. As an example of the constraints we will generate, let us consider our points-to sets again. In P1, for O1, we set its corresponding identifier to be larger or equal to the word size 4 multiplied by some offset. And we set it to be less than the word size multiplied by the offset, that is, its possible minimum value, plus the number of bits in the minimum number of words required to represent P1, plus some tolerance. That is, M1 is in some range, which is the minimum number of bits required to represent P1 and some tolerance if necessary. Then, we do the same for O2 and M2, and ensure that the offset is greater than or equal to 0. We repeat this for O1, O3 and O4 in P2, and O2 and O5 in P3. We then ensure that all the identifiers are unique. Finally, we hand this over to the solver and ask it to minimize the tolerances. This integer programming formulation gives us a good idea of what we are looking for and an optimal solution. However, it is expensive to solve, and especially scales far worse than just performing the PointsTo analysis with a subpar mapping. Thus, we look for more approximate but still effective techniques like hierarchical clustering. Hierarchical clustering is a technique popular in data mining communities which aims to cluster objects bottom-up according to some measure of distance such that closer objects appear together in smaller clusters. Let us consider this example of points on a plane, and let's say we want to cluster them according to the Euclidean distance. While the Euclidean distance gives us a measure of the distance between objects, it does not give us a distance between clusters, so we need a so-called linkage criterion. Let's use the single linkage criterion. which is that the distance between two clusters is the smallest distance between any member of one cluster to any member of another. To begin, we assume each point is in a cluster containing itself. First, we choose the two clusters or points with the smallest distance between them and cluster them together. V and X are as close to each other as W and Z are, so we pick V and X at random. Next, the closest are W and Z, so they are clustered. Now the closest two clusters are that containing just Y and that containing W and Z according to our linkage criterion, because W and Y are the closest points not in a cluster together already, so we cluster them together. Finally, there remain two clusters, so they are clustered together to end the process. The result is a dendrogram, a tree where leaves are individual objects and parents progressively form the clusters they are a part of. We can see immediately that Y, for example, is closer to W and Z than it is to V and X. Those were just points on a plane. Let's now apply this to the objects in the PointsTo sets of the auxiliary analysis. We first need to define the distance between two objects. We define it as the minimum number of words required to represent any PointsTo set in which both objects appear in as a bit vector. That is, the size of the smallest PointsTo set they both appear in the best case scenario. Now, to perform the clustering, we first build a distance matrix which encodes all distances between objects. We then choose a linkage criterion and perform the actual hierarchical clustering described previously, and the result is a dendrogram. With a dendrogram in hand, we initialize some counter to 0 and perform a depth-first search. At each leaf, which contains some object, we map that object to whatever the counter currently is and increment the counter. After this whole process, we will have a mapping where objects which appear in the same PointsTo sets are hopefully closer than before. That is due to our measure of distance between objects. Though not as effective as the integer programming solution, it is extremely fast and still gives plenty of benefit. There are a few ways we can improve this process. Firstly, we realize that objects which do not appear in a PointsTo set together would not affect each other's mapping. The difference in identifiers can be infinite and it will have no bearing. We separate objects into so-called regions and say two objects are in the same region if they appear in a PointsTo set together. We can then cluster regions separately. This is good because clustering, depending on linkage criteria, can be quadratic, so clustering smaller regions saves time. This isn't necessary, however, for our problem, since for our problem, clustering is extremely fast. More importantly though, we can save space as the distance matrix is quadratic in size and can get quite large. Furthermore, regions with fewer objects than the word size can have their objects mapped arbitrarily. Clustering will not improve the result, as any PointsTo set with objects in such regions will require just one word. For an optimization focused on the actual result, the lowest identifier in a region should always start at a word-aligned boundary. Let's take a look at an example of why. Imagine we have two regions with OA, OB, and OC in R1 and OD, OE, and OF in R2. With the mapping presented, PointsTo sets with objects in R1 can always be represented in one word. For R2, however, we may need one or two words. Obviously, this isn't optimal as there are only 3 objects in R2. Instead, let's consider a new mapping where the first identifier is aligned on a word boundary. Identifiers in R1 start at 0 and those in R2 start at 4. Now the PointsTo sets with objects in R1 always use one word as before, but so do those in R2 without much effort. We have implemented our approach in LLVM-based PointsTo Analysis framework SVF. We have not changed the base SFS algorithm, and our auxiliary analysis staging the main flow-sensitive analysis is a flow-insensitive Anderson's analysis. For clustering, we use the very capable fast cluster. In all our tests, at worst, the entire clustering and mapping process takes about 10 seconds. For linkage criteria, we try 3, since it is so fast, and pick the one with the most promise. Finally, our word size is 64, as we run these tests on a 64-bit machine. Here, we have the number of words required to represent all PointsTo sets in the theoretical, potentially impossible best case, in the original naive mapping, and then when mapping with clustering using single, complete, and average linkage. The best mapping for the auxiliary analysis is chosen at runtime and is shown in bold. Always, this turned out to be the best mapping for the main analysis. The final column shows a reduction of the bolded word count against the word count using the original mapping. On average, we reduce the number of words required by over 5.5 times. In all, on average, our work provides a moderate speedup of about 1.3 times and a memory reduction of over 2.35 times using core bit vectors and clustering over standard unclustered bit vectors. With that, I conclude our discussion on compacting PointsTo sets through object clustering. Our approach reduces the size of bit vector represented PointsTo sets in staged PointsTo analyses where the auxiliary analysis soundly over-approximates the main analysis. Our implementation can be found on GitHub. Thank you.